Now the speaker of the coming talk is Dr. Zhong Xiaohui, and from Fudan University. And the title of his talk is FuXi, Weather Forecasting System. And this paper wins the FSA award in the section of mathematical modeling and simulation. And now let's welcome Dr. Zhong Xiaohui to give a talk.
Thank you. And I feel honor and a pleasure to talk about our work on Fuxi weather system. I'm Xiaohui from Fudan University. So conventionally, the weather forecast. This slide shows how the weather forecasts are generated conventionally. So you have meteorological observations from different instruments like satellites, radar, ground stations, and shape. They all go into the processes called the data assimilation to generate the initial conditions for your numerical weather prediction model. And this model is a physics-based model. It consists of two uh, major parts. One is called dynamic core that used to solve the atmospheric equations on motion. And another one is the parameterization schemes. Those are used to resolve those subgrid scale physical processes like radiation transfer, um, clouds, turbulence, and so on. So it has uh, it has been evolved over uh, 7 decades, and the advantages of NW models are very clear. It can generate the physically consistent output because it basically made of what we know about the atmosphere. So it's physically understandable and interpretable, and can be applied to either globally or any part of the world without any training. But it also has very clear several disadvantages. So we know those nowadays the high computing resources all around the world are mostly used to. A lot of those high computing resources are used to run those NWT models. So we know so each day operationally takes thousands of CPU cores or even more to run an NWT model to deliver as a daily forecast. And we are now getting more and more observational data from satellites and radars. But although the NLP model's performance gets substantially improved after we first launched the meteorological satellites back into 1990s, but now the performance does not get the speed of the we didn't get the expected improvement from NLP models nowadays, although we are getting more and more observation data. Also, the forecast accuracy all around the world is not the same. Usually, over those regions like African regions or South American regions where we don't have enough observations, the forecast accuracy is lower compared to those regions, for example, Europe, North America, or East Asia. So there it, it so the global disparities in forecast accuracy exist. And now we are so so AI is actually reshaping the global landscape of weather forecasting. So before the year 2022, uh, all those conventional NWP models are developed and run by those national meteorological agencies because it's very complicated system, and you need a lot of human power and computational resources to do this job. So um, also um, you need people to take care of different observation instruments. You need people to take care about different uh, people have different expertise to take care of different physical parameterization schemes, and you need people to do the data assimilation. So a lot of work has to be done. So that's why only those countries I listed here are mostly developed countries. And after 2022, there this increasing number of the AI-based weather forecasting model that achieves comparable or even superior statistical performance relative to those conventional NW models, like um, like NVIDIA, Google's DeepMind, Microsoft, and also some research institutions like UCLA, FuXi from Fudan University. That's where our group is, and Fengwu from the Shanghai AI Lab. Those, so you can see that the AI-based models, forecasting models, actually reduce compared to conventional models. AI-based model is much simpler. So in terms of the number of lines of code that's used to develop the NW models, the AI-based model is much simpler. And thanks to the abundance of data we have in the meteorology, we have quite a lot of very well organized data set that can be easily used by these AI modelers. So that's and we don't know about the future right now, but I think in the future the complex will be more and more parties that join this AI for weather forecasting. So this is a very brief timeline about the weather forecast, the development of machine learning based weather forecasting models. So ever since the NVIDIA released ForecastNet in 2022, people start to realize that the AI-based model has the potential to outperform the conventional NW models. And before that time, it's not, most people don't believe this. And after that, the paper that get us here is the FuXi mid-range weather forecast that is released in the June 2023, and it is the first machine learning model that achieves the 15-day global weather forecast. So in terms of the model structure, it is a cascaded model architecture. So it's not only have one model, it actually consists of three models that optimized for three different forecast windows from 0 to 5 days, 5 to 10 days, 10 to 15 days. It has a total of 4.5 billion parameters. It can generating a 15-day, 6-hourly global weather forecast, and its accuracy matches the example mean of ECMWF ENS. ECMWF is the state-of-art physical model so far, and we have made this model openly available for any people to download and use this model. And also, to test how those models work operationally, the CMA, the China Meteorological Agency, launched this competition called AI Large Models for Weather Forecasting Demonstration Program. In short, AIM FDP. We also participated in this competition. They wanted to, so instead of judging the models by their testing data, all those models are run operationally daily since the competition begins maybe in last year. It's still running right now, the program. Actually, you can look at how those model performs from their website. So this FuXi is also has ranked #1 overall since the competition starts. So weather forecast is an area that the people can actually try and test every day that to see how good your model is, and not just by looking at how it performs over the testing data. And also there are some third-party evaluation, for example, by the ECMWF, by the Google Weather Bench 2. FuXi is also the performance of the FuXi is also similar to what we presented in our paper. So FuXi FuXi only has the 6-hour temporal resolution, the temperature resolution is not sufficient enough for many applications. So that's why we further developed this called 2.0 version to for more practical applications. So we develop the FuXi 2.0 consists of two models. One is a 6-hourly model similar to the FuXi 1.0, and another is 1-hourly model that interpolates the 6-hourly forecast into 1-hourly forecast, so that the number of autoregressive steps used to generating the entire 10 or 15-day forecast does not change too much, and we can still guarantee the model has a relative continuous forecast. And so for practical applications, we include more variables in our outputs, such as the 10-meter, the 100-meter wind speed for wind energy forecast, and solar irradiance for solar power forecast, and oceanic variables for marine shipping, and so on. And it is a very relative preliminary version of coupled atmosphere ocean model with some ocean surface information. And this coupling is quite important for tropical cyclone forecast because tropical cyclone involves the process not only from atmosphere but also from the ocean. So this slide shows that across those three application domains, from renewable energy to aviation we mostly evaluate cloud cover, and marine shipping, those variables are related to ocean waves. And we can see compared to the ECMWF model, we have lower RMSC, and lower RMSC indicate better performance, and higher anomaly correlation coefficient suggest also better forecast. And not only we provide better meteorological forecast, when those meteorological forecasts are going to the actual applications, for example, whether we can get more accurate wind power forecast. We see from the right figure, we tested on at the two wind farms, and we see that we get better accuracy for the wind power forecast by using our wind speed forecast. And as I mentioned earlier, that the model coupled some ocean surface information. So we want to see whether those coupling can help the models for performance for tropical cyclone forecast. We see that for tropical cyclone track, so here the green lines are the FuXi 1.0 without ocean coupling, and the red lines are the 2.0 version with ocean atmosphere coupling. We see that in terms of the tropical cyclone track, there is not much improvement. And in terms of the TC intensity, for example, the mean sea level pressure and the 10-meter wind speed, we see that we get the green lines or the red lines shows lower RMSC for the intensity. So it tells us that by coupling atmosphere and ocean, we can get some enhancement for the tropical cyclone intensity. And this is not the end of the story for the tropical cyclone forecast, because you can see that all those models are developed using a standardized data set called ER5. ER5 and we see from this is double y-axis plot. So the black lines in the first row indicates the IB track, which we can believe as observations for tropical cyclone. The observed tropical cyclone has overall average wind speed around 30 something meter per second, and the TC wind speed in the ER5 data is only around 20. So that means the training data we used for our model has much lower intensity compared to the observations, and that's one of the key and also and also suggest some potential for the future improvement. We can try to improve the data that we use to train our model by we can generate the more more accurate training data by ourselves using those NWE models. Okay, so all those FuXi model 1.0 or FuXi 2.0 are purely data driven. That means just use a transformer and you feed in data and then tune the model to get you the best performance. It doesn't involve any physics at all, but it may learn some physics from the training data because the training data, your ER5 is generally use physics-based models, but it doesn't have explicitly physical constraints within the model. So that's why we and many previous studies trying to incorporate physics are mostly trying to incorporate the dynamic core that I mentioned earlier that to solve the atmospheric equations. Those equations can be written. So they're basically trying to solve those equations with an ODE solver in their model. It's actually get their it incorporates like these equations are mostly for the advection, for the atmosphere advection, but it also makes those model relatively slower. So you lose the advantages of an AI being an AI models to be much faster than NMP models. So those models are much slower and doesn't account for any physical processes within the model explicitly. So that's why we come up with this idea. We developed FuXi RTM that we use deep learning models to emulate the radiative transfer processes within the NWP models. So this deep learning based RTM is basically a surrogate for the traditional radiative transfer schemes. The reason we make it a deep learning model instead of using the original physical based RTM model is the deep learning model can be used as a differentiable physical regularizer that we can put and we can jointly train it with the FuXi model. So in this loss equation, is not only we have we have the supervision for the atmosphere parameters. We also supervise how good the model perform for those radiation flags that's output by the DRRTM. So by incorporating this physical constraints, the model performance gets much improved. See the left bottom figure. The blue line, the blue color suggests better performance after we incorporating these radiation schemes, and especially for the surface albedo, which is very much related to the radiation. The performance gets the improvements is up to 15%. And also the FuXi RTM demonstrates a superior energy conservation compared to the baseline models. So the left bottom plot, this time series plot, shows how the energy conservation compared to the ground truth. So we have much lower differences compared to the baseline model if we incorporate these physics schemes. Okay. So now, previously, in the previous slides, I mostly talk about the deterministic forecast, and however, we know the atmosphere is chaotic due to but the forecast is uncertain due to the chaotic nature of the atmosphere, and we usually need to not only to do the forecast, we need to give the uncertainty estimate for our forecast. And to do that, we usually achieve it by running an ensemble forecasting. So ensemble forecast is is done in conventionally is you run model multiple times with different initial conditions that you predict the initial condition in a certain way and to give you different start points for your models, and you can also perturb the model physics within your undoubtedly models. Here we do it in a data-driven way, and we develop this called the FuXi ENS, and it can provide the 15-day forecast with 6 hourly temperature resolution at 0.25 degree spatial resolution. It consists of two main components. One is the forecast model. It shares the similar structure with the FuXi model. And another is the perturbation model. The perturbation model is a VE-based model that can, so given the certain initial conditions, you can generate a Gaussian distribution, and then we can sample from the Gaussian. We can sample from this Gaussian distribution and add the sampled noise to the initial conditions to generate a perturbed initial conditions. And these perturbed initial conditions will feed back into the forecast model to generate one forecast. So the number of times we do this sampling, so as long as we so the number of times we do this sampling equals to the number of times we can get the different forecast. So this is how we do it in the FuXi ENS. And traditionally in the VE model, we usually the reconstruction loss is a L1 loss, and here we replace the L1 loss with a CRPS loss. Is not only measure the forecast directly with the target, just point by point measurement. It also measures the distribution of the forecast with the target. So that's how. And if it is a deterministic forecast, then the CRPS turns into a MAE mean error, mean absolute error. So this gives us a improvement. So here the plot shows the FuXi ENS if it is trained with L1 loss in black line compared to the FuXi ENS if it is trained with CRPS loss in the red line. We can see the red line gives us lower CRPS. CRPS is a very important metric for ensemble forecasting. Also give us a lower RMSE for the ensemble mean. You can generate better ensemble spread compared to if we use L1 loss. So the most recent model developed by the ECMWF called the AIFS CRPS is they also use the similar metric, similar trick as we do. They use the CRPS loss in their training. And this is how the model performs compared to the state-of-art physical model in the ECMWF ENS. So we evaluate three very important variables in the weather forecasting. The 500 geopotential tells us how the large scale circulation is, and the 850 hectopascal wind speed in the middle column, and the 2-meter temperature in the right column. And from we compared three metrics: RMSE, ACC, and mean bias error. So in terms of the RMSE and ACC, we basically outperform the ECMWES across most lead times and variables. And we also do some significant testing to see if we get to see if they actually pass this to see if the improvement is statistically significant. So this red dots indicate where those time steps we significantly outperform the ECMWF-ENS. So for the ensemble forecast, the most important evaluation is also another important evaluation is for the probabilistic forecast metrics. So we compare the similar variables, but in terms of the probabilistic metrics, and ROCSS in the middle is trying to evaluate how model performs for the extreme weather. So for the extreme weather case, we also generate better forecast for compared to the ECMWF ENS. But for the spread scale ratio in the bottom, spread scale ratio tells us how good our model's spread spread represents the model's error. So if, for example, forecasting this is one of the most important metric because you don't know the future in ahead, but you know the spread based on your forecast. You know how your different forecast members different from each other, and you want this spread to represent the potential error from your model. So if this SSR value is closer to 1, that means you can basically estimate how much error in your model's future forecast from your ensemble spread. So that represents your forecast uncertainty. Here you see that although we have smaller error compared to the ECMWES, but we still have a a way to go compare in terms of this SSR. We have SSR not as close to 1 as those ECMWMES in the blue line. We also compare our model with one of the SOTA model, not only in machine learning, whether ensemble forecasting, that's the GenCast that just get published in Nature last year. And GenCast is a model that really hard to beat. Although we basically developed at a similar time, uh, but they also yeah. So we compare our model with their model as well. So in terms of statistical metrics, we are mostly quite similar, but they outperform us mostly most notably in terms of the 2-meter temperature. They have the lower CRPS and better metrics for the extreme forecast, and their SSR is closer to 1 than our model does. And there's still some room for the future improvement for our model. For example, we can try to learn from their most recent work, like FGN. They incorporated they train the model with different seeds and to account for the model's uncertainty. Yeah. So one of the most important extreme weather is the tropical cyclone. So we also evaluate our model for the tropical cyclone forecast. So in terms of the air, so the red the red the red line red color indicates the ECMWES. The blue color is FuXi ES. The FuXi also has smaller error, has lower error compared to the the SOTA and physical model, but it also has lower spread. That's the issue that we mentioned earlier. And in terms of there are also some other extreme events. For example, the heat wave. We compare we evaluate heat wave events in 2018. FuXi shows very comparable performance to the ECMWES in terms of this heat wave event. And for the prediction of the 2018 Hurricane Florence, the FuXi achieved, in terms of spatial pattern, the FuXi has better spatial pattern compared to ECMWES, but it tends to underestimate the, the precipitation intensity. Here shows in the sorry in the in the in the contour. The speed the precipitation intensity is much underestimated by FuXi forecast, but it's also overestimated in the ECMWF forecast. Okay, so all those AI-based models that I talked earlier are still not independent or standalone system because they still need those NWT models to run in parallel to provide them with the initial conditions to run the forecast. So that means although AI model is very fast, you can still not get rid of the NWT models because you use them to give you the initial conditions. So that's the key we need That's the one key problem that we think we should address in the after we finish development of FuXi forecasting model. But there are also quite a lot of challenges with the traditional data assimilation workflow. For example, although a lot of observations has much higher resolution than our forecast model. For example, we have in China alone, we have more than more than 50,000 of ground stations, and the radar data has the spatial resolution about as high as 1 kilometer or even 0.5 kilometer. But the model resolution is very coarse. It means maybe the highest the model resolution is only 10 kilometer. So you need to do the data thinning. You need to uh, to to coarsen your high resolution data to lose some information, and you need to estimate how much error in your observations. And also, a lot of observations are not direct measurements of your weather parameters, are not measurements of temperature, pressure, or wind speed. They're actually measurements of radiance or reflectivity. So you need to convert your model parameters, weather parameters, from the physical space into the observation space to align them to calculate the error to trying to minimize the error in the model forecast. And a lot of, once you know the error, some systematic error in observation, you do the bias correction. And also for satellite observations over the cloudy region, the forecast the observations are not quite good. You need to do the cloud detection to remove those observations where you observe clouds. So the entire data processing is quite complicated. Let me explain why only uh, only the developing countries has the human power to do all those jobs, because it's quite. And another disadvantage is quite a lot of useful observations are discarded in this process. So this is the major challenges with the traditional data assimilation flow or workflow. So that's why we come up with this new system called the FuXi weather. Uh, this paper has been just recently accepted by the Nature Communication, and so this model is follow the forecast and the simulation framework, as similar as the traditional weather forecasting system. We have a forecast model and another data assimilation model to do the data assimilation. So the data assimilation model we call it FuXi DA, and we use the ER5, the standard the gold standard data set to train both the evaluation model, assimilation model, and the forecast model. And this framework can do the 6-hourly DA data estimation and the forecasting cycle, and to generate 10-day weather forecast at 0.25 degree resolution. And this is basically model structure in FuXi DA. So the most simple, most important contribution of FuXi DA is greatly simplify the workflow compared to the traditional DA. So we no longer need to do any observation operator, because for observation operator you have to develop each of the one observation operator for different instruments. So think about how many satellites you have, and think about how many satellite instruments you have. This is a quite troublesome job, and for every new satellite you have to do this once again to be able to use the observation from that satellite. And we don't need to do the error estimations for the background observations. And this observation metrics, error metrics, and the background error metrics are huge. And you have to do in the traditional DA, you have to do a lot of math to simplify the representation of those huge metrics. And we don't need to do that using AI model, because all those observations and background are converted into the latent space of the model, that you can align them in, just as treat them as equal in the latent space. And so this model can do the bias correction by encoding the spatial temporal information to automatically correcting the biases in the observations. And it can jointly optimize the analysis and the forecasting beyond the optimization window you have in the traditional 40-watt system. Because in a traditional 40-watt system, you can optimize your analysis and the forecast within a time window that you have observations. But that time window is usually only limited to maybe 10 hours or 12 hours. And you can't wait for longer time, because if you wait for long, then you won't get forecast in time. And in AI model, we can do this optimization for longer lead time to improve our forecast. And this is very computationally efficient. It is thousands of faster for inference compared to traditional DA model. And this is this plot shows an example of the observations we assimilate into our system for one time. And although it basically consists of 5 microwave instruments aboard 3 polar orbiting satellites, and also includes some GNSS radio calculation data all around the world. So although the yellow dots looks like very formidable a lot, but compared to the number of grid points we have over globally, it only consists, it's quite sparse. Only 0.15 50 is less than 0.03%, 0.06%. And for this data simulation work, we directly assimilate raw brightness temperature data. So those observations can be put into the model without any pre-processing. And those data also has high resolution. We have to interpolate them into regular 0.25 degree similar to match with the FuXi model resolution. And we use the point pillar pre-processing to map the GNSS data to 2D grid. This point pillar method is a very classical method in the pre-processing of the point cloud data in computer vision. And for the FuXi weather training, so we know that the background forecast that being fed into the data simulation model varies with the quality varies with time. So in order to mimic the operational scenario, we simulate different quality background fields by using FuXi model forecast of different lead time, initialize the ER5. And we do this joint optimization of analysis and forecast with this latitude weighted L1 loss function. And after we know that we cannot get as good as the quality as the ER files, because ER5 actually use way more satellite observations than we have. They also not only have satellite observations, they have a lot of ground observations as well, and it has more than 90 satellite instruments. Compared to us, we only have 5 satellite instruments in our study. So we have to fine-tune the FuXi model with using the analysis that generated by this data estimation model to have a better performance for the forecast. And when we evaluate a standalone forecasting system, we usually break it down into 2 parts when we evaluate analysis. So in terms of analysis, we see this figure shows 3 pressure level. From the left column to right columns are 300 and 500 and 850 hectopascal from the higher latitude to altitudes to the lower altitudes. And the rows 1 through 5 are the 5 atmospheric variables we predict at these pressure levels. And those black lines are the FuXi weather analysis without incorporating the background forecast. And we want to see if we just use the observations without using any background forecast, how the analysis look like. And the red lines are the FuXi weather analysis by incorporating the background forecast. That's what the conventional model do as well. And the blue lines are the baselines to show how good the analysis are. And these are forecasts, FuXi forecasts, but initialized with ER5. So you see that from this plot, the RMSE of analysis field is relative higher at lower altitude. Higher, the RMSE is better at 850 hectopascal because we have more information coming from the satellites at this low altitudes compared to the higher altitudes. And by incorporating the background forecast, so the red line has smaller MSC compared to the black line. That suggests the importance of incorporating a background forecast because background forecast provides you a base to start with. If you just rely on observations, you will get higher oscillations. You will get more unstable results. And this is how the forecasts look like. In a standard way, we usually evaluate the model forecast against their analysis, or in another term, their initial conditions. So the green lines, the green dash lines, the green lines here are the forecast evaluate against FuXi weather's analysis, and the blue lines are ECMWF evaluate against its own analysis or initial conditions. They both show very small initial error, which is expected. But if we evaluate our model against ER5, that shows in red and blue and the black lines, they show higher initial MSC because our initial conditions are not as good as ER5. So the starting point, you get worse results. But overall, in terms of the model's skillful prediction for those very important variables, especially for the 500 hectopascal geopotential, we achieve even longer skillful prediction time than the SOTA physical model ECMWF, which will be able to get 9.5 days skillful prediction lead time for this geopotential. And another surprising result we get is we get a better performance over the Central Africa, because Central Africa or the Africa region is a region that we don't have much ground observations, and both our model and the physical model can mostly rely on those remote sensing data, for example, satellite data. So for those regions that we have a very similar starting point, and against for these regions, it costs a lot of money and human power to install those ground stations to provide the more accurate ground station data. So if we can provide them with better forecasts by just using satellite observations, that will be a very good for them. So FuXi weather in red and green lines are providing a smaller RMSE error for those important variables, and we also further break down the RMSE to the mean bias error, which is the systematic biases of the model, and a standard deviation of error, which is the random part of the error. We can see not only for the model not only reduces the systematic biases, but also reduces the random errors compared to the physical model. So this is the time series of some example initialization. So FuXi weather also shows much closer alignment with the benchmark, with this reference compared to the ECMWF over Central Africa. So so although FuXi weather is also a purely data-driven data simulation system, we wonder if it can be physically consistent or can be physically explainable. So we do this called the data deline experiment. We remove certain or specific uh, instrument from the observations to see how much the error increase in the analysis. So we see that if we remove this MWTS, which mostly observe the temperature, we can see a much a higher increase in error in temperature compared to the humidity. And we know that this MWHS is mostly measure the moisture. So by removing this MWHS, we have a larger error growth in the relative humidity compared to temperature. And this ATMS is observing both observation moisture and the temperature. So by removing it, we have much bigger error in both temperature and humidity. Although all those instruments doesn't measure the wind speed directly, but the wind speed is related to the moisture because the tracer effect. So for those instruments that directly measuring the moisture, like MWHS and ATMS, we can see a big error impact from by removing those two instruments. So that means that although it's a purely data-driven model, it still learns some correlation between all the observations and the certain physical variables. Yeah. So in the end, I want to say this plot, this figure, this slide shows a family of the FuXi model system. Not the FuXi is not no longer just one model, not no longer a medium range weather forecasting model that won us this award, but it's actually becoming a modeling system that covering different time scale from the nowcasting 0 to 12 hours to medium range 0 to 15 days to subseasonal. We have FuXi subseasonal to seasonal weather for prediction that also that is one of the CMA's AI-based system called FengShun. It has been run operationally in CMA National Climate Center and providing us forecast uh, to it has been run operationally. And we wanted to do the climate projections to see how the climate how to give us more accurate climate projection under different carbon emission scenarios pathways. So um, so I want to say here is not trying to say that we are doing a lot of work. We are trying to see find the most interesting and the problem in this field to try to address them in using machine learning, trying to improve the forecasting to give us better forecast by using machine learning techniques. Yes, that's all my presentation today. Thanks.
Thank you for the talk. I'm Mark Stefik from the United States. I'm not a climate specialist, so I have only very general questions for you. I wonder what you think is the hardest problem you're facing in the weather forecasting, and what is the most important kind of forecast that you need to be able to make. Thank you.
Yeah, that's very good question, and we have also been thinking about this problem. I cannot say um, for sure what is the hardest problem. I think this is being discussed, and it's also I can evolve with time because all those models that we have seen today, we have witnessed today, are just trying to apply the machine learning techniques into the field and get results. So So in the future those are like I could say easier to something that easier to get, something that easier to get in short time. But in the future, there are bigger problems like how the how much predictability. If we can actually push the predictability of the weather by using machine learning models, because traditionally we think the weather is only predictable within 15 days. So beyond the 15 days is no longer predictable, although you can still do the forecast and give you some results, but it's still not predictable because of our understanding of because of like the butterfly effect. But if we can actually address those problem or by push the limit of our understanding of the predictability of the weather, I think that's one of the biggest problem in the future. Did I answer your question? Thank you.
So any other questions? So I'm also want to ask some maybe general question. Okay. So you mentioned many versions of the FuXi model. I want to know. So what is the FuXi version in the paper? In the paper you win the award.
Okay.
Because
it's the first version of FuXi with cascaded
1.0.
Yeah, that's the first version.
Okay, the first version.
Yes. Use the cascaded model architecture to generate the 15-day weather forecast. Because we use this by using this cascaded model architecture, we can mitigate the accumulation of forecast errors during the auto-regressive process.
Now the best version is FuXi 2.0.
I can say that again 2.0 has been improved upon the FuXi 1.0, and I think for now there are different version of FuXi model. Not so FuXi 2.0 I can say the best model for the deterministic forecasting, but not for the ensemble forecasting. For ensemble forecasting we have FuXi ES. So it have different purpose. And for sub-seasonal forecast we have FuXi S2S that's also get published last year in Nature Communications. Yeah.
Okay. Thank you. So if there is no more questions, and now let's conclude this talk, and thank you all for coming. Yeah.
Thank you.